We now made sure that IOStream is included multiple times. It's even redundant because I already place it here and also place it directly above my header.h. It's your preference. Depends how widely you're going to be using this. But my preference perhaps at the beginning would be to keep this include outside this my header. Again, this is not a very specific example, so it should be fine if it included directly in dummy.cpp because it's such a well-known header file. All right, so now access to cout is not an issue or should not be an issue. So let's go build again. Take a look at what's happening here, it was able to do everything without, oh, okay, sorry. I added the function and now we're able to compile, but remember the next thing is to be able to, perhaps we can say, we can print array before and after, right? So we can print it twice. You can say std cout cout before init, right? And use semicolon here, and we can say also now that this is after init. Okay. So our intent is basically create an array, print its content before initialization, call initialization, call it again, and do a second display. Okay, build, and it simply says that identifier not found. This print array identifier is not found simply because print array is defined in one CPP file. Main CPP is a different CPP, and therefore it just right here, it has no clue what print array is. What I forgot is that such as I did with initialize array, I remember to do the prototype, and now I will copy the header of this print array function, go to my header.h and add this as a prototype, make sure I add the semicolon at the end. Save everything, right? You can actually use file. There's like a save all or control shift S, which is very helpful. I do this by, routinely by habit. So anyway, but now I should be able to say build, and it builds fine in my case. And then if I just run it, right? So here it is. Before init and after init, it prints what was expected, 10, 12, 13, and 14. Please let me know if you have any questions or issues or anything related to what we have. So quick overview is that we are working with the header file, which declares dummy, which we're no longer even using, right? But it's still someplace, I assume, right? And then we have initialize array, which are two function prototypes, and ARR is a name of the, apparently, the ARR represents an array, and I know this by looking at the square bracket on the right-hand side, an array of 5 integers. Okay. But just the knowledge that array is passed indirectly by address and not by a copy of the array. One more thing I would like to discuss here with you. Let me clean this up. So, if from our code, you can see that what we do in our code, first we call print array, then we call initialize array, and then we call print array again in terms of our own functions. So just to be sure that, let me just erase this for now, right? So what happens again, we say print, we call print first, and its stack frame is assembled, its local ARR variable is initialized with address of the original array, and we do some processing. Of course, the executable code is somewhere else, right? So we have this loop over here that loops and basically initializes it with 10, 11, 12, 13, 14, and then we're done. And when we return, the stack frame is destroyed. Okay, it's no longer available. We return from print as if we never called it. Okay, so that's the mechanics of it. Then we call initialize. So after the initial print, then we call initialize, and everything begins again. The copy of this, the address of the first element of the array is copied over to stack memory. Then print, I'm sorry, this time it's init. Init is I messed it up. I should have said print first, not init. But so that should not be part of our first function call, right? So we call init, and init then organizes its own stack frame, does the work, does initialization, returns. When it returns, all of this is lost, right? All of this is gone, and what remains still in memory is only the stack frame for main, because main is still working, main is still executing. Then again we call print, right? Again we invoke print on that third line, and again we pass the array address, right? And we organize its stack frame if it's using additional variables, and I think it does, right? Right here in the implementation of print we have index. So index is another local variable. So this is ARR and this is index, and this index is used locally, right? So this print array is working. And then when it's done, this when it returns, its stack frame is destroyed and everything is gone, okay? And then main says return 0, and its stack frame and everything inside of it is destroyed, and we're out. The program ends. So basically, when you have, say that I wanted to do a number of function calls, like function 1, function 2, function 3, function 4, if I made these function calls in the chain type of manner, like function 1 calls function 2, function 2 calls function 3, and then eventually they return, then the stack frame would grow like this. The stack will grow, right? So this would be the stack frame that belongs to function 1, function 2, function 3, function 4, right? And then function 4 returns, okay, and then maybe function 3 returns, but function 2, before it returns, could actually call function 3 2 more times, function 3, right? So the whole thing will start again. Stack frame for function 3 is created. As soon as it returns from function 3, it's destroyed. Another call to function 3, it is reproduced again in memory, in stack memory function 3. So it does its own thing. Again, when this returns, right, it's gone, then this is gone, then this is gone. I'm assuming main is still somewhere present in that stack frame, and when that's gone, it's gone. So every function call requires some passing of parameters on the stack, and then creating the stack frame. And then, of course, the local variables are also working in this local variable scope. But occasionally, you have perhaps these parameters are pointers, and pointers give us access to other objects elsewhere in computer memory. So pointers, or in our case, address of that array, was an example of indirect access from one function to another function, or in fact any other part of our program, whatever we want to access. Essentially, pointers give us access to any part of the program, any data. And we begin to demonstrate this type of arrangement with this small demo program that we have. Okay, number of things that I want to address. We still have the question, how many elements to initialize, number one. And I still want to go back to ARR and talk about its specifics and what it really is.